So one thing that I want to remind you of, it's not something that's new, but now that we're going to talk about your brain and spinal cord a little more specifically, I just wanted to remind you where you find gray and white matter. So if we take a look at your brain, which is one of the two components of your central nervous system, you'll see that this outer layer is gray. Now, if you look at the picture, what we're trying to represent is that we've taken someone's brain and we're looking at a cross section through it. So this line right here is showing you, like if we sort of took a slice right there and we looked at it, this is what we would see. The white matter, which I'll make a different color, is the section that's on the inside, more or less. Now, could someone remind us what the difference between gray and white matter is? Like what they're made out of, or something about nerve conduction in gray versus white matter? So how about which of the two has myelin, gray or white? White. White matter has myelin. So which of the two conducts impulses faster, white or gray? White, because it has myelin. Now, if we look at the spinal cord is a bit different. In the spinal cord, you will see, some people say it looks like a butterfly, that internal section of the spinal cord. That section, that is the gray matter. The other part, the part that goes around it, so all of this stuff, that's the white matter. So the spinal cord and the brain are sort of opposite in terms of where the gray matter is and where the white matter is. We saw the gray matter before because that is where the interneuron in a reflex arc is located. It's in the gray matter in the middle of your spinal cord. Looks like a butterfly, maybe like an H. Now, the brain and the spinal cord are the two main pieces that make up your central nervous system. So we need to know how they are protected. If you have ever touched a brain before, I have, you will touch one tomorrow. They're not tough, they're squishy. The ones that we have at school are preserved, so they're a little bit tougher than normal. But the consistency of a brain before preservation is not tough. It's mushy. It's mushy like a sort of half-cooked potato, like you could squash it and ruin the tissue pretty easily, and I did a few times, ruin things before I preserved them. So we need some structures that are going to protect this really important but really delicate tissue. So we're going to talk about protection. The first thing I want to highlight is bones. If we were to take a section of somebody's skull and the first few layers of tissue underneath it, this is what it would look like. The bone of the skull is solid, and it protects your brain very specifically against physical damage. Perhaps you've heard the expression that someone is hard-headed, and it's supposed to mean that they're stubborn, but your head really is hard. That is some really strong, really tough, really solid bone, because it's protecting basically the most important thing that you have in your whole body underneath it. Aside from the bone that you have in your skull, you also have a few layers of tissue. These three layers here, all of the ones that have matter as part of their name, you don't need to know the three different names, not in this course anyway, but it's the dura, the arachnoid, and the pia. These are three layers called collectively the meninges. If a person has meningitis, this is the tissue that's affected. These are pieces of elastic tissue. So they're not solid and hard like bone is. Elastic tissue means it's a little more flexible, a little more stretchable. Now if you look, there are 3 layers of tissue, and they're written in the order that they appear. So there's a layer that's closer to your bone, one in between, and then one that covers the surface of the brain. But this elastic tissue provides a barrier. Between brain and blood. Now you might wonder why on earth you need a barrier between your brain and blood. Blood has a lot of things that your brain really, really needs a lot. But there's a lot of things that are in your blood that would hurt your brain tissue if it touched it directly. So blood vessels flow through your brain, but blood itself, the plasma in your blood cells, don't or aren't supposed to touch the tissue of your brain. So in the title here, the blood-brain barrier, or BBB, is made up in part by these meninges. Now, just because they're providing a barrier doesn't mean that now it's impermeable to everything. Some substances have to be able to cross this barrier. So, things like oxygen and glucose can cross, but unfortunately, any liposoluble drug, so something that is soluble in lipids, meaning it could get across membranes, is also able to get across. So for example, it could be something as sort of mundane as caffeine, or it can be something as serious as heroin. There are drugs that can cross the blood-brain barrier, which would explain why they have effectiveness, because they can get in and affect your brain tissue. Now over here on this side, there's what we call the subarachnoid space. Sub means below. And arachnoid is referring to one of these layers, specifically this one. Now the fact that it's called the subarachnoid space is probably not the most important detail, but what I find here is something called cerebrospinal fluid, or CSF. So you don't just have bone and tissue, you've got a fluid to help cushion your brain. This fluid does 2 things. It transports substances, but it also cushions against shock. So, if we were to ask what protects your central nervous system, I would say there are 3 things: bone, meninges, and cerebrospinal fluid. Now, does anyone want to ask any questions about those 3 things that offer protection? So there are some other things that are labeled here just so that you can see them. For example, you can see where the blood vessels are. If you look at where they are, they're in between the arachnoid and the pia. So your brain tissue is separated from blood vessels by those meninges. Now, if we take a look at the structures that make up your brain overall, we could kind of divide your brain into 3 sections. We'll start at the bottom and at the back with the hindbrain, then we'll go up to the middle, then up to the top. So the hindbrain is made up of three basic structures. First, the cerebellum. So the cerebellum, the word literally means little brain or tiny brain. And if you look over here where the cerebellum is, it's this structure. It looks like a tiny extra brain attached at the back of your brain. That's where its name came from. The cerebellum's job is unconscious control of coordinated movement. So notice that it's unconscious. These are for things that you're not thinking about. So the first few times you tried to ride a bike, you were thinking about what you were doing. You were thinking about where your feet were and where you had to put your hands. And you were very aware of whether you were balanced enough or whether you felt like you were leaning. But chances are, if you know how to ride a bike now, you don't have to think about what you're doing when you're riding the bike. You just get on and go. But I just remember this because last year was really the year my kid learned to ride her two-wheel bike with no training wheels. And I forgot how hard it is to learn how to ride a bike when your muscles don't know how they're supposed to move to keep you balanced. So anything that involves unconscious control of coordinated movement, anything that requires any kind of coordination that you can do without thinking about it. So some of you, maybe riding a bike isn't your thing, but you have learned how to skate, or you've learned how to ski, or you know how to snowboard, or some other thing that was really hard the first time you did it, but you know what, I still am not good at snowboarding. I want my 2 feet to be separate from each other, and the fact that they have to stay together really messes me up. But I can ski because I can move my feet independently. So that's your cerebellum's job. The medulla is the next one. We'll make the medulla blue here. If I look where it is, sometimes it's hard to identify a structure just based on its position. So here, I'd like to specify that the medulla is below the pons, but above the spinal cord. So if I were to go down, the next thing I would see is the spinal cord. If I were to go up, the next thing I would see is the pons. Now, what's the medulla's job? Chances are you've heard about this before. The medulla controls automatic, involuntary functions. So for example, your heartbeat or breathing. Any of these automatic functions that your body accomplishes to keep you alive, like your heart beating and like you breathing, your medulla can control. Now the pons is the next one. The pons, I think, is easier to pick out because it's the bump. Now, some of you might know another language, maybe French or Spanish or any of those languages. In French, a pont is a bridge, and this literally is the bridge. Looks like a little thing that you go over. So the pons, we'll just call it the bridge. That's not its name. That's just me giving you something to compare it to. What do bridges do? They let things get from one side to the other. So what does your pons do? It acts as a relay. So it relays a couple of things. It relays the hindbrain to the midbrain. And the midbrain will be the next thing we take a look at. It also relays the left and right sides of your brain, because it's in the middle. So it's relaying what is in this hindbrain section, so information coming from the medulla and the cerebellum up to the next part of your brain, which will be on the next slide. Now together, these three structures sometimes get referred to as the brain stem. If you think of what a stem is, that the bottom holds everything else up, this is the stem of your brain. Now, so far, does anyone want to ask any questions about the base of your brain? So if we keep looking at the same picture, the midbrain is the next section, and it's really its own piece. So we'll just highlight it here. The midbrain, like its name suggests, is in the middle. So it's not the lowest part of the brain, it's not the highest part of the brain, it's in the middle. And I always like to tell people it is right above the pons. What shape is it? It's a weird, indescribable shape that I couldn't give a name to. So I like to describe its position rather than its shape. The midbrain's function is similar to the pons. It relays, very specifically, audio and visual information. And because we're talking about visual information, there's also a specific thing about eye movement and just generally skeletal muscles. So it relays information about audio and visual stimuli, so hearing and seeing things, and about the movement of your eyes and the movement of your skeletal muscles. So we have the hindbrain, which is at the base and at the back. We have the midbrain, which is in the middle. And then the last of the three sort of major sections of your brain is the forebrain. The forebrain is at the top and then at the front. Now, there are a lot of structures that make up part of your forebrain, and we're just going to look at a select few of them. One of them is the thalamus. So, where's the thalamus? Well, if we're looking at a picture of a brain, the thalamus is right above the midbrain. Same thing as the midbrain. What shape is it? It kind of depends who's drawing the picture. Some artists represent it just as a circle, some as an indescribable shape, but it's more its position than anything that's important. Your thalamus, in terms of function, is the great relay station. So a lot of these structures are to relay information to other parts of your brain, and your thalamus more so maybe than anything else. It is for sensory information, very specifically. So if we take a look at that compared to the midbrain kind of focused on audio and visual, but this would include audio information, visual information, taste information, touch information, so other senses as well. Your hypothalamus, so hypo means less than, it's sort of below and in front of the thalamus. Now the hypothalamus, I always identify by what it's attached to. So even though we're not talking about them yet, you have some structures called your pituitary glands. They look like, it looks like a little piece that's dangling when we're looking at a picture of a brain. And if I can identify where the pituitary gland is, it's attached to the hypothalamus. So wherever the little dangly piece is, the thing that came before it in the brain structure is the hypothalamus. The hypothalamus regulates your internal environment. So if we think about your internal environment, we would be talking about things like blood sugar, like levels of other things in your blood, like calcium, like metabolism. We will talk about your hypothalamus in great detail in chapter 13 when we talk about all of your hormones. So even though it's just one little piece of the brain here, it will come back with great importance when we talk about how your body produces hormones. The last thing we have is the cerebrum. So the cerebrum is probably what you think of when you're thinking of a brain. It's the wrinkly, grayish looking part. It takes up about 4/5 of the mass, so about 80% of the mass of your brain is this, the cerebrum. Now, if any of you are X-Men fans, that machine thing's called Cerebro. That's the part of the brain that we're identifying with here, is this part. Now, your cerebrum does a whole bunch of things, but anything where you are conscious, anything where you have to do some sort of interpretation of information happens in the cerebrum. Now those are big words that encompass a ton of things, and I'll be a little bit more specific about some of the sections of your cerebrum. But that was just like 30 new. So if we take a closer look at the cerebrum, which is 80% of the mass of your brain, there are a few things that we could distinguish. First, there's the cortex. So this is the outer gray layer. Cortex means bark. So just like the bark is on the outside of a tree, your cerebral cortex is the outer layer of your cerebrum. The cerebral cortex is the part of your brain that is involved with thinking. So anytime you are thinking about something or you are aware of something, it is the cerebral cortex that's at play. Now you have a structure called the corpus callosum. On the picture, and I'll just highlight it here, it's right here and right here. So if we're looking at your brain from the side, it's kind of the shape of a banana, sort of. And if you're looking at it from the front, it kind of looks like a little heart. But what this is white matter linking the left and right sides. There's a lot of research about this corpus callosum and what happens if it's damaged. Sometimes people have their corpus callosum damaged purposefully. Some people suffer from seizures where nerve impulses are transmitted too much or with too high of a frequency. And there's a lot of research about this structure and the role that it might play. Now, because it connects the left and right sides of your brain, if your corpus callosum was damaged, it would mean that it would be harder for information to get from the left side to the right side of your brain, which you might not think matters, but you have two hemispheres, the left and the right, and they seem to have more distinct functions. The left side of your brain is the side that deals with logic or sequential thinking. This happens, then this happens, then this happens. It's the side that tends to deal with math and with language. So words, math, calculating things, being logical and sequential. The right side of your brain tends to be the holistic side, where instead of thinking of first this, then this, then this, this is the big picture side of the brain. This is the artistic This is the visual spatial side. So when we're talking artistic, we could be talking about color, we could be talking about other types of visual arts, we could be talking about music and musical arts, so art doesn't mean just drawing. The visual spatial thing, this is the side of your brain that's usually better at processing and seeing how structures can be made in space. So if you've ever taken one of those quizzes, like the How Smart Are You quizzes, and it says, here's a bunch of shapes, which one of them is the one that's in the picture, and you have to maybe mentally rotate the shape or imagine what it would look like upside down, that's when you need visual spatial intelligence. Now, I'm not saying that one side of the brain only does that and that's it, but based on brain research, it seems like the left side deals more with those things and the right side more with the others. Now, we can also divide your cerebrum. Whoops, that is not what I meant to do. Let's get back to where we were. Let's go. There we go. We can also divide your cerebrum into lobes. So if we look at your cerebral cortex from the outside, we can section off parts of the brain, and it would be the same on the left and right hemispheres. So we're just looking at one side of the brain here. There are 4 basic lobes. So we'll start up here with this. This whole section is the frontal lobe. Now, you wouldn't have to distinguish, not on a diagram anyway, very specifically some of the substructures of the frontal lobe. For example, that Broca area and the motor strip. Your frontal lobe is involved with a few specific functions. For example, motor control. That means that this is the section of your brain that has cerebral cortex dedicated to movement. Oops, if I could spell the word movement. So if a person were to have damage to their frontal lobe, movement might be an issue because this is the part of your brain that controls it. Because it controls movement, it also plays a role in speech, because to speak, you have to be able to move muscles and move them very specifically to produce specific sounds. This is also the part of the brain that is involved with memory, personality, and reasoning, sometimes called critical thinking. So if we had to pick which part of the brain makes you who you are, it's this part, the part that's at the front. Now if we move around over here, this little section here is your parietal lobe. And if you can see at the very front of the parietal lobe is this strip of cortex that's for sensory information. So this is your somatosensory information processing center. Now, what does somatosensory mean? Well, soma means body, and sensory means sensory. And a lot of what we're talking about here are things that you would detect on your skin: touch, temperature, pressure. In the next chapter, we'll talk about some of the specific receptors that you have for those things. I'm leaving out some of the sensory information because you have other parts of your brain that are specifically dedicated to that. Now, if we move on down to the back of the brain, in this section, let's use black here, this is your occipital lobe. And its function is vision. Everything to do with vision. Processing visual stimuli, understanding what you're seeing. And then over here, we have your temporal lobe. And if you imagine where your temporal lobe is from the outside of your head, it's on the side, right where your ear is. Your temporal lobe is the primary area for auditory information. And because one of the main types of auditory information we receive is language, this is the sensory speech area. So notice the difference. This isn't the area that controls you being able to say words. This is the area that's involved with you understanding and detecting words that you are hearing. So your frontal lobe lets you make sounds. Your temporal lobe lets you understand sounds. If you notice on the picture, there's a couple of areas, the Broca and the Wernicke area. Those have been extensively studied in terms of language function. People who have damage to the Broca area can understand language but can't produce it. People who have damage to the Wernicke area can produce language, but it is nonsensical. They can say words and they have no problem making sounds, but it sounds like gibberish because they don't have the sensory speech, understanding speech section functioning. Now those are the four lobes. The way that they are divided on this picture is not something that you have to memorize. If you remember that frontal is at the front, parietal is at the top, occipital is at the back, and temporal is on the side where your ear is, that's the most distinction you would have to make. You wouldn't have to be able to perfectly trace the edge, let's say, of one lobe to the next. That's something that's beyond the scope of our course. Now the last thing I just wanted to show you is this. If we take the parietal or the frontal lobe specifically, they both have a strip, the motor strip and the sensory strip, that controls you being able to move and you being able to feel things. But the way your cerebral cortex is divvied up is not proportional. I didn't put this picture on your study guide, but it's just part of the title of this section. There is way more cortex devoted to your hands and your face than other parts of the body. So this little representation, a homunculus, perfectly formed miniature human, represents if our bodies were to proportion with how much of our brain is devoted to controlling them. You would have a massive face with really, really big mouth and lips and tongue because there's lots of sensory receptors on your tongue and in your mouth. Plus, you need to control the muscles of your face very, very delicately so that you can say words, so you can make facial expressions. And then you'll notice he has really, really big hands because your hands are often what you're using for very delicate control. You can do things like button a button with your fingers. Sometimes people who have maybe lost a hand or maybe were born without one, their sensory cortex gets redistributed so that the part of their body that they are using most has more cortex devoted to it.